The journey of a photon across the universe. Long before a photon begins its incredible journey across the universe, its story begins in one of the most powerful environments known to science, the heart of a star. Deep inside the blazing core of the Sun, temperatures reach nearly 15 million degrees Celsius. Pressures are so immense that atoms are crushed together with unimaginable force. In this extreme environment, the most fundamental process that powers the universe takes place: nuclear fusion. Here, hydrogen, the simplest and most abundant element in the cosmos, is transformed into helium. 4 hydrogen nuclei collide and combine through a chain of nuclear reactions. In the process, a tiny amount of mass disappears. But that mass does not simply vanish. According to the famous equation discovered by Albert Einstein, mass and energy are 2 forms of the same thing. When a small amount of mass is lost during fusion, it is converted into energy. That energy is released in many forms. One of those forms is light. And from that burst of energy, a photon is born. A photon is one of the most fascinating particles in physics. It is the fundamental particle of light, a tiny packet of electromagnetic energy that travels at the fastest speed possible in the universe. Once created, a photon immediately begins moving at the speed of light, which is about 300,000 kilometers per second. At that speed, a photon could travel around the entire circumference of Earth more than 7 times in just 1 second. Yet, for a photon born deep inside a star, the journey is not as simple as racing straight into space. The core of the Sun is incredibly dense. It is packed with countless particles, protons, electrons, atomic nuclei, and energetic radiation moving in every direction. The interior of a star is not empty space. It is more like an incredibly crowded storm of particles, constantly colliding and interacting. As soon as the photon is created, it collides with nearby particles. Instead of escaping instantly, the photon is absorbed by an atom. A fraction of a second later, it is emitted again. But when it is re-emitted, it travels in a new direction. Almost immediately, it collides again. Absorbed, re-emitted, scattered, again and again. Inside the Sun, this process repeats an astonishing number of times. The photon moves only a tiny distance before another interaction sends it in a completely different direction. Its path becomes something like a cosmic pinball game. Scientists call this process a random walk. Even though the photon always moves at the speed of light, its progress outward through the star is incredibly slow because of these countless interactions. In fact, it may take a photon tens of thousands or even hundreds of thousands of years to travel from the core of the Sun to the star's surface. That means the sunlight reaching Earth today may have begun its journey long before human civilization existed. Perhaps even before the first human ancestors walked across the planet. For the photon itself, however, time behaves in a strange way. According to the laws of relativity, time slows dramatically for objects moving at extremely high speeds. For something traveling exactly at the speed of light, time effectively does not pass at all. From the photon's perspective, if such a perspective could exist, the moment of its creation and the moment of its arrival somewhere else in the universe happen instantly. But to the rest of the universe, the photon's journey unfolds over vast distances and enormous spans of time. Eventually, after countless scatterings inside the star, the photon reaches the outer layers of the Sun. These layers are less dense than the core. Particles are spaced slightly farther apart. The photon now has a better chance of traveling longer distances before colliding again. Slowly, gradually, the photon works its way outward through the Sun's interior, layer by layer, collision by collision, year after year. Finally, after a journey that may have lasted hundreds of thousands of years, the photon reaches the visible surface of the star. This glowing surface is known as the photosphere. From here, the photon will finally be able to escape. Beyond this point lies open space. No longer trapped inside the dense interior of the Sun, the photon will now begin the true adventure of its existence. A journey that may carry it across the entire solar system, across the Milky Way Galaxy, perhaps even across the vast emptiness between galaxies, all at the fastest speed allowed by the laws of physics. The photon has traveled for hundreds of thousands of years just to reach the surface of its star. But the greatest part of its journey is only just beginning. After an incredibly long and chaotic journey through the dense interior of the Sun, our photon finally arrives at the outer boundary of the star's visible surface, a glowing layer astronomers call the photosphere. This thin layer marks a remarkable turning point. For hundreds of thousands of years, the photon has been trapped in a turbulent maze of particles. Inside the Sun's interior, matter is so dense that light cannot travel very far before encountering another particle. Each interaction sends the photon bouncing in a new direction, turning what should be a straight journey into a slow and complicated wandering. But here, at the photosphere, conditions begin to change. The density of particles drops dramatically compared with the Sun's deeper layers. Atoms are still present, of course, but they are spaced far enough apart that a photon now has a real chance to travel freely. For the first time since its birth, the photon is close to open space. The surface of the Sun is not a solid surface, like the ground beneath our feet on Earth. Instead, it is a vast ocean of glowing plasma, a hot, electrically charged gas made of free electrons and atomic nuclei. Seen through powerful telescopes, this region appears textured and alive with motion. Huge convection currents rise and fall constantly, bringing hot material upward and sending cooler material downward again. These enormous cellular patterns create what astronomers call solar granulation. Each granule may be hundreds or even thousands of kilometers wide. Within them, hot plasma rises toward the surface, radiates energy into space, and then sinks again in darker lanes between the cells. Our photon emerges into this restless sea of glowing plasma. Around it, countless other photons are being created every moment through similar nuclear processes deep within the star. The surface of the Sun radiates an immense flood of light into space. Every second, the Sun releases more energy than humanity has used in its entire history. And within that flood of energy, our tiny photon prepares for its escape. The photon is emitted from an atom in the photosphere after a brief interaction. For a moment, it travels outward. Nothing blocks its path. No particle absorbs it, no collision redirects it. For the first time since its birth, the photon travels uninterrupted. It leaves the Sun. Instantly, it enters the near vacuum of space. Compared with the dense interior of a star, space is astonishingly empty. Even in the inner regions of the solar system, particles are separated by enormous distances compared with those inside a star. For the photon, this means freedom. It now moves through space at the full, unobstructed speed of light, racing outward in a straight line. Behind it, the blazing surface of the sun glows with the light of trillions upon trillions of other photons, making similar escapes every second. Some of these photons will travel toward distant planets. Some will fly out of the solar system forever. Some may wander through the Milky Way Galaxy for millions of years before encountering anything at all. Our photon begins its own path across the solar system. Directly ahead lies open space. But space, although empty, is not completely featureless. Surrounding the sun is an invisible bubble created by the continuous stream of charged particles flowing outward from the star. This wind of energetic particles is known as the solar wind. The solar wind expands in all directions, carrying magnetic fields far into space. It forms a vast region known as the heliosphere, a protective bubble that surrounds the entire solar system. The photon passes through this region effortlessly. Unlike charged particles, photons are unaffected by magnetic fields. Nothing in the solar wind can slow it down or alter its course. The photon continues racing outward. If its path happens to aim toward Mercury, the smallest and closest planet to the Sun, it will reach that world in just over 3 minutes. If it is traveling toward Venus, the journey will take about 6 minutes. And if the photon is heading toward our home planet, Earth, it will arrive in approximately 8 minutes and 20 seconds. That short journey across space may seem insignificant compared with the hundreds of thousands of years the photon spent wandering inside the Sun. Yet those 8 minutes represent an extraordinary crossing of space, a journey across nearly 150 million kilometers. Every second, countless photons make this trip. They warm the oceans, they illuminate the sky, they drive the chemical reactions that allow plants to grow and produce oxygen. Without these photons from the Sun, life on Earth would not exist. But our photon's destiny is still unknown. It might strike the surface of a planet. It might bounce off an asteroid, drifting quietly between the orbits of Mars and Jupiter. It might continue outward, passing the majestic rings of Saturn, the distant blue world of Neptune, and the icy bodies scattered through the Kuiper Belt. Or it might leave the solar system entirely, venturing into the vast darkness between stars. At this moment, the photon's path is simply a straight line through space. There are no maps, no destinations, only the endless openness of the universe. And so, having spent countless ages escaping the interior of a star, the photon finally begins the greatest journey it will ever make. A journey across the cosmos, a journey that may last seconds or millions of years. Having finally escaped the blazing surface of the Sun, the photon now moves freely through the quiet vacuum of space. For the first time since its creation deep within the star, nothing blocks its path. No dense plasma surrounds it. No particles scatter it randomly in new directions. The photon travels in a straight line at the incredible speed of light, the ultimate speed limit of the universe. Behind it, the Sun continues shining with unimaginable power, releasing an endless ocean of light in every direction. Ahead lies the vast structure of the solar system, a family of planets, moons, asteroids, and distant icy worlds that all orbit the star from which the photon was born. The first world the photon might encounter is Mercury, the innermost planet of the solar system. Mercury circles the Sun at an average distance of about 58 million kilometers. From the Sun's perspective, it is extremely close. If the photon happens to be traveling in the direction of Mercury's orbit, it will reach the planet in just over 3 minutes. Mercury is a strange and extreme world. It has almost no atmosphere to protect its surface. Under the relentless light of the Sun, temperatures on the sunlit side of Mercury can soar above 400 degrees Celsius. If our photon were to strike the rocky surface of this small planet, it might be absorbed by a dark mineral in the ground. Its energy could become heat, warming the stone by an immeasurably tiny amount. Or it might bounce off the surface and continue its journey in a new direction, reflected into the depths of space. But in our story, the photon does not collide with Mercury. Instead, it continues outward through the inner solar system. Not far beyond Mercury's orbit lies another world, one that shines brilliantly in the skies of Earth. This is Venus, often called Earth's sister planet because it is nearly the same size. Yet Venus is far from welcoming. The planet is wrapped in a thick atmosphere of carbon dioxide and clouds of sulfuric acid. These clouds reflect much of the sunlight that reaches them, making Venus one of the brightest objects in the night sky. If the photon were to strike those clouds, it might scatter many times among the swirling droplets of acid before eventually escaping again. Some photons that enter Venus's atmosphere are trapped by its powerful greenhouse effect, helping to maintain surface temperatures hot enough to melt lead. But once again, our photon slips past this world without interaction. It continues its silent flight outward. The next destination along this path may be the blue planet, the world where oceans cover most of the surface and life flourishes beneath a protective atmosphere. After traveling roughly 8 minutes and 20 seconds from the Sun, the photon reaches the orbit of Earth. From space, Earth appears as a delicate sphere of blues, whites, and browns. Swirling clouds drift across vast oceans, while continents stretch across the surface like giant islands. If our photon's path intersects the planet, many different outcomes are possible. It might strike the upper atmosphere and scatter off a molecule of nitrogen or oxygen. That scattering process is part of the reason the sky appears blue during the day. Other photons might penetrate deeper into the atmosphere and reach the ground. Some are absorbed by the leaves of plants, where their energy drives the remarkable chemical process known as photosynthesis. Through this process, plants convert sunlight into chemical energy, producing oxygen and sustaining much of the life on Earth. Other photons strike the oceans, warming the water and powering the circulation of Earth's climate. Still others reflect off clouds or ice, bouncing back into space. Every moment, trillions upon trillions of photons from the Sun reach Earth and shape the delicate balance that allows life to exist here. But our photon continues its journey without touching the planet. It races past Earth's orbit, leaving behind the bright blue world and the thin atmosphere that glows softly in sunlight. Beyond Earth lies another, smaller, rust-colored planet, Mars. Mars is colder and drier than Earth, with a thin atmosphere and vast deserts of iron-rich dust that give the planet its reddish appearance. If the photon were to strike Mars's dusty surface, it might reflect into space with a faint reddish tint, contributing to the soft glow that telescopes observe from Earth. In ancient times, humans looked at that reddish glow in the sky and imagined a planet associated with war and fire. Today, we know Mars as a world of towering volcanoes, enormous canyons, and frozen polar caps. But once again, our photon passes Mars without encountering it. The journey continues. Beyond Mars stretches a region filled with countless rocky fragments, the asteroid belt. These objects are remnants from the early days of solar system formation, pieces of material that never combined into a full planet. Some asteroids are only a few meters across. Others, like the dwarf planet Ceres, are hundreds of kilometers wide. Yet even here, space is incredibly empty. The distances between asteroids are enormous compared with their sizes. The photon slips easily through this region. Beyond the asteroid belt, the solar system begins to change. The rocky worlds of the inner system give way to enormous gas giants. Far ahead lies the largest planet of all, Jupiter. But the photon has not yet reached that distant realm. For now, it continues speeding through space, moving farther and farther from the star that created it. Behind it, the sun slowly shrinks into a brilliant disk of light. Ahead lies the outer solar system, a vast domain of giant planets, icy moons, and mysterious distant objects. The photon's journey is still only beginning. Beyond Jupiter lie worlds that take years, decades, even centuries to orbit the sun. And beyond them lies the great darkness between the stars. Our photon continues its silent flight into that immense and beautiful unknown. The photon continues its silent flight away from the warm glow of the sun. Behind it, the bright star that created it slowly shrinks in the vast darkness of space. What once filled the entire sky now becomes a brilliant disk, then gradually a distant point of light. Yet even as it moves farther away, the sun's influence still dominates the region around it. Gravity from the sun governs the motion of everything in the solar system, from the smallest grains of dust to the largest planets. Countless objects continue circling the star in stable orbits, forming a complex and beautiful structure that stretches billions of kilometers into space. Our photon now approaches the realm of the giant planets. The first and largest of them is Jupiter. Jupiter is truly enormous, more massive than all the other planets combined. It dominates the outer solar system with its powerful gravity. Its swirling atmosphere forms colorful bands of clouds that wrap around the entire planet. Within those clouds, rage storms far larger than Earth itself. One of the most famous of these storms is the Great Red Spot, a colossal hurricane that has been raging for centuries. If our photon's path happened to intersect with Jupiter's thick atmosphere, it might be scattered among the planet's towering cloud layers. It could reflect off ammonia crystals drifting high in the atmosphere, helping create the brilliant patterns of light that spacecraft cameras capture when they pass nearby. But space is vast. Even a giant planet like Jupiter occupies only a tiny fraction of the enormous regions surrounding the Sun. Our photon passes through Jupiter's orbit without encountering the massive planet. As it travels onward, the solar system begins to feel even more spacious and quiet. The next great world along the photon's possible path is Saturn, perhaps the most elegant planet in the entire solar system. Saturn is famous for its magnificent rings, enormous bands of ice and rock that encircle the planet like a delicate cosmic halo. These rings are made of countless particles, some no larger than grains of sand, others as big as mountains. If the photon were to strike one of these icy fragments, it might reflect brightly, becoming part of the soft glow that makes Saturn's rings shine so beautifully when sunlight reaches them. Yet once again, our photon does not collide with any of these objects. It continues forward, slipping quietly past Saturn's orbit. Farther still lies the distant blue-green world of Uranus. This planet rotates in a very unusual way. Instead of spinning upright like most planets, Uranus is tilted dramatically, almost rolling along its orbit around the Sun. Because of this tilt, the seasons on Uranus are extreme. Each pole can face the Sun continuously for decades before finally turning away again into long darkness. The photon glides past the orbit of Uranus without slowing. Beyond Uranus lies the final giant planet, Neptune. Neptune is a cold and distant world where powerful winds roar through the atmosphere at incredible speeds. These winds can reach more than 2,000 kilometers per hour, making them the fastest planetary winds known in the solar system. Even though Neptune is so far from the Sun, sunlight still reaches it. But by the time it arrives here, that light has spread out across enormous distances. The Sun appears much smaller and dimmer in Neptune's sky. Still, even this faint sunlight is enough to illuminate Neptune's deep blue clouds. Our photon now crosses the orbit of this distant planet. At this point, it has traveled billions of kilometers since leaving the surface of the Sun. Yet the solar system does not end here. Beyond Neptune stretches a mysterious region filled with icy worlds, a vast ring of ancient objects known as the Kuiper Belt. This region contains thousands, perhaps millions, of icy bodies left over from the early days of planetary formation. Some of them are small and irregular. Others are large enough to be classified as dwarf planets. One of the most famous of these is Pluto, once considered the 9th planet of the solar system. Pluto orbits the Sun in a long, elliptical path far beyond Neptune. Its frozen surface is covered with nitrogen ice, methane ice, and strange, mountainous landscapes sculpted by extreme cold. But the photon does not pause to explore this distant world. It continues moving outward. The Kuiper Belt gradually becomes more sparse as distance increases. Eventually, the region transitions into an even larger and more mysterious structure, the Oort cloud. The Oort cloud is believed to be an enormous spherical shell of icy objects surrounding the entire solar system. These objects are remnants from the formation of the planets billions of years ago. Some of them may drift tens of thousands of astronomical units from the Sun. Occasionally, gravitational disturbances from passing stars send one of these icy bodies inward toward the Sun. When that happens, the object may appear in the inner solar system as a long-tailed comet glowing in sunlight. But our photon is not bound by gravity. It does not orbit the Sun. It simply continues traveling outward in a straight line. Eventually, it passes beyond the outer boundaries of the Sun's magnetic influence, the distant frontier where the solar wind meets the thin gas between the stars. This boundary marks the edge of the Sun's vast protective bubble, known as the heliosphere. Beyond this point lies true interstellar space. The photon has now completed its journey across the solar system. Behind it lies the star that gave it life. Ahead stretches the enormous expanse of the Milky Way Galaxy, filled with hundreds of billions of other stars, each with their own planets and perhaps their own stories. The photon races onward into that immense darkness. Its journey has taken only a few hours in the time measured by the universe. But the path ahead could last millions or even billions of years. Because once a photon escapes its star and enters the galaxy, its journey may continue across unimaginable distances. And this small particle of light, born deep inside the Sun, has now begun a voyage that could carry it across the entire cosmos. Our photon has now traveled farther than any of the planets that circle the Sun. The giant worlds, Jupiter, Saturn, Uranus, and Neptune, are now far behind it. Even the icy bodies of the Kuiper belt have faded into the darkness. Yet the photon is still inside the enormous sphere of influence created by the Sun. This invisible region is called the heliosphere, a vast bubble carved into the surrounding galaxy by the continuous flow of charged particles streaming away from the Sun. These particles form what astronomers call the solar wind, a steady current of electrons and protons traveling outward in all directions. For billions of kilometers, the solar wind pushes against the thin gas that fills interstellar space. The result is a protective cocoon surrounding the entire solar system. Inside this bubble, the Sun's magnetic field dominates the environment. Outside it lies the wider Milky Way Galaxy. Our photon continues racing outward at the speed of light, unaffected by magnetic fields or charged particles. Unlike atoms or spacecraft, photons do not slow down or change direction because of these forces. They simply move forward, straight, unstoppable. Far ahead lies a distant boundary where the solar wind begins to weaken. As the particles spread farther and farther from the Sun, they gradually lose strength. Eventually, they collide with the thin gas of interstellar space. This distant frontier is called the heliopause. Here, the influence of the Sun finally gives way to the environment of the galaxy itself. Human spacecraft have only recently begun reaching this boundary. One of the most famous explorers of this region is Voyager 1, launched from Earth in 1977. After more than 4 decades of travel, it finally crossed the heliopause and entered interstellar space. But for our photon, reaching this boundary takes only a matter of hours. After escaping the Sun, the photon continues outward, crossing the vast distances of the solar system with ease. Eventually, it arrives at the heliopause, the outer edge of the Sun's domain. In that moment, the photon officially leaves the solar system. Ahead lies the immense emptiness between stars. Beyond the heliopause, the environment changes subtly. The solar wind fades. The magnetic field of the Sun weakens. Instead, the photon now moves through the thin gas and dust that fills the spaces between stars, a region astronomers call the interstellar medium. Although we often describe space as empty, the interstellar medium is not a perfect vacuum. It contains atoms of hydrogen and helium drifting slowly through the galaxy. Tiny grains of cosmic dust float among them, microscopic particles made of carbon, silicates, and other elements forged in ancient stars. These particles are extremely sparse. In many regions of space, there may be only a few atoms in each cubic centimeter. Compared with the dense interior of the Sun, this environment is unimaginably empty. For the photon, this means it can travel enormous distances without encountering anything at all. Years may pass, decades, centuries, and the photon may never interact with a single particle. From its point of origin, the Sun now appears as just one star among many. If someone were standing on a distant planet far from the solar system, our Sun would appear as a small point of light in the night sky, no brighter than many other stars scattered across the Milky Way Galaxy. The photon continues its journey through this enormous stellar city. The Milky Way itself contains hundreds of billions of stars. Each of them shines with its own light, producing countless photons of their own. In a sense, the galaxy is filled with rivers of light, flowing outward from every star simultaneously. Our photon is just one tiny traveler among these vast cosmic streams. Yet even such a small particle can carry information across enormous distances. Astronomers on Earth rely on photons like this to understand the universe. The light that reaches our telescopes carries clues about the temperature, composition, and motion of distant stars and galaxies. Every photon is a messenger, a tiny packet of information traveling through space. Our photon continues forward through the interstellar medium, crossing distances that stretch across trillions of kilometers. Behind it, the solar system fades completely from view. As the photon travels deeper into the Milky Way Galaxy, it may eventually pass near other stars. The nearest stellar neighbor to the Sun is Proxima Centauri, a small red dwarf star located about 4.2 light-years away. A light-year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. For our photon, crossing that distance takes exactly the same amount of time, 4.2 years. During that time, the photon moves continuously at the speed of light, never slowing, never stopping. If its path carries it close to Proxima Centauri, the photon might pass through the faint outer regions of that star's planetary system. Astronomers have discovered that Proxima Centauri hosts at least one planet, Proxima Centauri b. This distant world orbits close to its dim red star and may lie within the star's habitable zone. If our photon were to strike that planet, it might reflect off its surface or atmosphere and continue onward. In that moment, a particle of light born in our Sun would briefly touch another planetary system. But the chances of such an encounter are extremely small. Space between stars is so vast that most photons travel their entire lives without ever striking a planet or even a grain of dust. Instead, the photon continues deeper into the galaxy. All around it, countless stars glow softly in the darkness. Some are larger and brighter than the Sun. Others are faint red dwarfs, barely visible across the cosmic distances. Many of these stars are surrounded by their own systems of planets. Entire solar systems drift silently through the galaxy, each with its own history and future. And our photon moves quietly among them. The longer the photon travels, the more distant its birthplace becomes. After millions of years, the Sun will have moved far from the place where the photon was born. Like all stars in the Milky Way Galaxy, the Sun slowly orbits the center of the galaxy. It takes roughly 230 million years for the Sun to complete one full orbit around the galactic center. During that time, the photon may have traveled across enormous portions of the galaxy. Perhaps it will eventually encounter a cloud of interstellar dust and be absorbed by one of its microscopic grains. Perhaps it will strike the surface of a distant planet, orbiting a star humanity has never seen. Or perhaps it will continue traveling through space for billions of years, eventually escaping the Milky Way entirely and entering the vast emptiness between galaxies. Once free from the gravity of the galaxy, the photon could travel across the expanding universe itself. It might cross unimaginable distances before finally interacting with matter again. Or it might travel forever, carrying with it a tiny piece of energy created deep inside the Sun, billions of years earlier. For now, the photon simply continues forward, a small particle of light moving across a universe that is far larger and more mysterious than any one star system. And its journey is only just beginning. Our photon has now left the distant outskirts of the Sun and its planetary family far behind. The solar system has faded into the enormous sea of stars that make up the Milky Way Galaxy. Here, the scale of the universe becomes almost impossible to imagine. The Milky Way is not just a scattered collection of stars. It is an immense spiral structure, stretching more than 100,000 light-years across. Hundreds of billions of stars orbit slowly around the galaxy's central core, forming graceful spiral arms that wind outward like the arms of a giant cosmic whirlpool. Our photon now travels within one of these spiral arms. This particular arm is known as the Orion Arm, a smaller branch of the galaxy where the Sun itself resides. From within the galaxy, these arms are not sharp lines, but broad regions filled with stars, nebulae, and vast clouds of interstellar gas. The photon continues forward at the unwavering speed of light. All around it, countless other photons stream outward from stars in every direction. Every star is a beacon, sending waves of light across the galaxy. Many of these photons have traveled for thousands, millions, even billions of years before crossing paths with our traveler. In the quiet darkness of space, the galaxy is full of these silent travelers. The photon glides through regions where stars are scattered like distant lanterns. Some are bright blue giants burning intensely. Others are small red dwarfs glowing faintly for trillions of years. One of the remarkable features of the Milky Way is how varied its stars can be. Massive stars live fast and die young, exploding in powerful supernovae. Smaller stars burn slowly, sometimes surviving longer than the current age of the universe. Yet, to the photon, these differences matter little. It continues forward in a straight line, unaffected by gravity unless it passes extremely close to a massive object. The space between stars is unimaginably vast. Even in the denser spiral arms of the galaxy, the typical distance between stars is several light-years. This means that our photon can travel for years, centuries, or even millennia without encountering anything at all. Yet the galaxy is not completely empty. Ahead lies one of the most beautiful and mysterious environments in the cosmos, a nebula. Far ahead, a faint glow begins to appear in the darkness. The photon approaches a vast cloud of gas and dust drifting through the Milky Way Galaxy. These clouds are known as nebulae, enormous regions where stars are born and cosmic material slowly gathers together. One famous example is the Orion Nebula, a spectacular stellar nursery located more than 1,000 light-years from Earth. Nebulae can stretch across dozens or even hundreds of light-years. Within them, cold gas slowly collapses under gravity, eventually forming new stars and planetary systems. Our photon drifts into one of these immense clouds. Inside the nebula, the environment is very different from the empty interstellar regions it has traveled through before. Here, the density of particles is still extremely low by human standards, but it is far greater than the surrounding vacuum. Hydrogen atoms drift slowly through the cloud. Tiny grains of cosmic dust float silently in the darkness. When photons from nearby stars strike these particles, the gas begins to glow softly. Some nebulae shine with beautiful shades of red, blue, and violet. These glowing colors come from excited atoms releasing energy as light. Hydrogen often produces deep red light, while oxygen can produce greenish or bluish hues. Our photon moves through this luminous fog. At any moment, it could collide with a dust particle and be absorbed, ending its journey forever. But the universe is vast. Even inside a nebula, particles are separated by enormous distances. The photon slips through the cloud without interacting. Around it, new stars are forming. Dense knots of gas slowly collapse under gravity, heating up as they shrink. Over millions of years, these regions may ignite nuclear fusion, becoming newborn stars, much like the Sun once did billions of years ago. If planets form around these new stars, they may eventually host oceans, atmospheres, and perhaps even life. The photon glides quietly through this stellar nursery, a place where future solar systems are taking shape. But the journey continues. Farther along its path, the photon may encounter something far more mysterious. At the heart of the Milky Way Galaxy lies one of the most extreme objects in the universe, a supermassive black hole known as Sagittarius A star. This object contains the mass of millions of suns, compressed into a region smaller than the orbit of Mercury. Black holes are regions where gravity becomes so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. But our photon is not heading directly toward this monster at the center of the galaxy. Instead, it passes through the outer regions, influenced by its immense gravity. Even though photons have no mass, gravity can still bend their paths. According to general relativity, massive objects warp the fabric of space-time itself. As the photon passes through this warped region, its trajectory may curve slightly. Astronomers call this effect gravitational lensing. Light from distant stars and galaxies can be bent around massive objects, creating distorted or magnified images when observed from Earth. Our photon's path may bend ever so slightly as it travels through the gravitational landscape of the galaxy. Yet it continues forward, escaping the pull of the black hole, because it never approaches close enough to be captured. Ahead lies more open space, billions upon billions of kilometers of silent darkness. After traveling through nebulae, past distant stars, and across the gravitational fields of massive objects, our photon continues drifting through the enormous structure of the Milky Way Galaxy. The galaxy is not static. Everything within it is in motion. Stars orbit the galactic center. Gas clouds drift and collide. New stars ignite, while old ones die. Occasionally, massive stars explode in spectacular supernova events, releasing enormous bursts of energy that briefly outshine entire galaxies. When such explosions occur, trillions upon trillions of photons are released into space. Some of those photons may cross paths with our traveler. Light from ancient supernovae, distant stars, and glowing nebulae flows constantly through the galaxy like invisible rivers. Our photon is now part of that vast cosmic current. Millions of years may pass as it continues its journey. The Sun, the star that created it, has moved far from its original location in the galaxy. The solar system itself continues orbiting slowly around the galactic center. Yet the photon travels onward, unaffected by these motions. Eventually, it may reach the outer regions of the Milky Way. Beyond that boundary lies the enormous emptiness between galaxies, a realm where distances grow even more unimaginable. If the photon escapes the gravity of the Milky Way, it may drift through intergalactic space for billions of years. Or it may eventually encounter a distant world orbiting another star, perhaps even a planet where intelligent beings are looking up at the night sky, wondering where the light they see has come from. And if that happens, the journey of this tiny particle of light, born deep inside the sun, may finally reach its destination. But for now, the photon continues its endless voyage through the vast and beautiful galaxy. For millions of years, the photon has traveled through the vast structure of the Milky Way Galaxy. Behind it lies the spiral arm where its journey truly began, near the quiet yellow star known as the Sun. That star, along with its family of planets, including Earth, has long since drifted far from the place where the photon was created. Stars in the galaxy are never still. They orbit slowly around the galactic center, completing one enormous journey roughly every 230 million years. But the photon is not bound to these orbits. Moving always at the constant speed of light, it travels in a straight path that ignores the circular dance of stars. Over time, that straight path carries the photon farther and farther from the dense regions of the galaxy. The Milky Way slowly begins to change around it. The bright concentration of stars that once surrounded the photon gradually thins. Spiral arms fade into more scattered populations of stars. The glowing nebulae and star-forming clouds become rarer. The galaxy's great rivers of gas and dust drift farther apart. Eventually, the photon reaches the outer halo of the Milky Way Galaxy. This region is very different from the crowded spiral arms. Here, stars are sparse and widely separated. Many of them are ancient, older even than the Sun, quiet remnants of earlier ages in the galaxy's long history. Clusters of old stars drift here like slow-moving islands in the cosmic sea. Astronomers call these structures globular clusters, great spherical swarms containing hundreds of thousands of stars bound together by gravity. Some of these clusters have been orbiting the galaxy for nearly as long as the Milky Way itself has existed. The photon glides past one such cluster. From afar, the cluster appears like a faint glowing sphere in the darkness, each tiny point of light representing a star. These stars burn steadily and quietly, some of them shining for tens of billions of years. But the photon does not stop. It continues outward. Soon, even these ancient clusters grow rare. The stars of the galaxy now lie almost entirely behind the traveler. Ahead stretches something far more mysterious: intergalactic space. From this distance, the Milky Way Galaxy itself begins to change appearance. What once seemed like an endless sea of stars now looks like a soft, glowing disk suspended in the darkness. Spiral arms curve outward gracefully from a bright central bulge. Dark lanes of dust cut across the starlight like delicate shadows. It is a breathtaking view. The photon has become an observer, leaving its own galaxy behind. Beyond this point lies one of the largest environments in the universe, the enormous emptiness between galaxies. And the photon is about to enter it. Intergalactic space is one of the quietest places in the universe. When the photon finally leaves the gravitational boundaries of the Milky Way Galaxy, the environment around it becomes even more empty than the interstellar medium it traveled through before. Here, the density of matter is extraordinarily low. Only a few atoms may exist in an entire cubic meter of space. These atoms form what astronomers call the intergalactic medium, a vast and extremely diffuse gas filling the spaces between galaxies. Most of this gas is hydrogen, the simplest element in the universe. It has been drifting through space since the earliest epochs of cosmic history, long before galaxies like the Milky Way were fully formed. For the photon, traveling through this region is almost effortless. Nothing blocks its path, nothing scatters it, nothing slows it down. Years pass, then centuries, then thousands of years. The photon continues forward, crossing distances so enormous that even light takes millions of years to traverse them. Behind it, the Milky Way Galaxy slowly shrinks into a distant spiral of faint light. Yet it is not the only galaxy in this vast darkness. The universe is filled with galaxies. Some are small collections of stars, only a few thousand light-years across. Others are enormous giants, containing trillions of stars. Our home galaxy belongs to a small gravitational family known as the local group. This group contains more than 50 galaxies, all slowly orbiting one another through space. The largest of these neighbors is Andromeda Galaxy. From Earth, Andromeda appears as a faint smudge in the night sky. But in reality, it is a massive spiral galaxy, even larger than the Milky Way. It lies about 2.5 million light-years away. For our photon, that distance represents an enormous journey. Yet time means little to light. The photon continues forward across the dark ocean between galaxies. Millions of years pass. Gradually, a faint glow begins to appear ahead. At first, it is almost imperceptible, just a subtle brightening of the darkness. But as the photon continues traveling, the glow grows stronger. Another galaxy is coming into view. It is the great spiral known as the Andromeda Galaxy. From a distance, Andromeda looks very much like the Milky Way. Its spiral arms stretch outward from a luminous central core, filled with billions of stars shining together. Massive clouds of gas drift between the stars, glowing faintly where newborn suns illuminate them. Dark lanes of cosmic dust trace graceful patterns through the spiral arms. Our photon approaches this enormous structure. If it enters the galaxy, it may travel among entirely new stars, stars that have never been seen from Earth. Many of these stars may host their own planets. Some of those planets may have oceans, atmospheres, and perhaps even living organisms looking up at the night sky. For a moment, the photon becomes part of the immense gravitational environment of the Andromeda Galaxy. Its path may curve slightly as it moves through the galaxy's gravitational field. It glides past enormous clouds of gas and regions where new stars are forming. Elsewhere in the galaxy, ancient stars drift quietly through space, their planets circling them in silent orbits. Yet even here, the photon may continue onward without interacting with anything at all. Because even inside a galaxy, the universe remains astonishingly empty. The photon continues its silent voyage. It has traveled across planetary systems, through interstellar space, across the enormous structure of the Milky Way Galaxy, and now through the dark ocean between galaxies. All of this began with a single moment deep inside the blazing core of the Sun, when nuclear fusion released a tiny packet of energy into the universe. That packet of energy became a photon. From that moment onward, it has never stopped moving, always at the same cosmic speed, always forward. Perhaps the photon will eventually collide with a grain of cosmic dust. Perhaps it will strike the atmosphere of a distant planet orbiting an unfamiliar star. Or perhaps it will travel forever, drifting through the expanding universe long after the stars that created it have faded away. In the end, The photon's journey is a reminder of something profound. Light connects the universe. Every star, every galaxy, every distant world communicates through streams of photons, crossing unimaginable distances. The light reaching our eyes when we look up at the night sky has often traveled for millions or billions of years before arriving. And somewhere out there, in the vast darkness, photons born in our own sun continue their journeys as well. Silent travelers carrying a small piece of our star across the cosmos. Their paths may stretch across galaxies, across billions of years, across the entire history of the universe itself. And their journey, like the story of the cosmos, may never truly end. After millions of years, drifting through the immense darkness between galaxies, the photon continues its silent journey through space. It does not grow tired. It does not slow down. Time, as living creatures understand it, does not exist for a photon. From its perspective, the entire universe is simply a path of motion. Far ahead, a familiar structure begins to appear. A soft spiral of glowing starlight, slowly growing brighter against the blackness of space. It is the Milky Way Galaxy. Across cosmic time, this great galaxy has continued its slow evolution. Stars have been born within enormous clouds of gas. Others have died in brilliant explosions. Spiral arms have shifted and rotated as billions of stars circle the galaxy's center. Yet its overall shape remains recognizable. A vast spiral disk floating within the cosmic ocean. The photon moves toward it. Soon, the galaxy's spiral arms begin to stretch across the darkness. Vast rivers of stars trace elegant curves through space, while dark clouds of dust weave delicate shadows between them. Within one of those spiral arms lies a modest yellow star. That star is the Sun. Around this star exists a small planetary family known as the Solar System. Rocky worlds orbit close to the Sun. Massive gas giants circle farther away. And among these planets is a remarkable world, one covered in oceans and wrapped in a thin, life-supporting atmosphere. This world is Earth. From space, Earth shines with an unusual beauty. Blue oceans cover most of its surface, reflecting sunlight back into space. Swirling white clouds drift slowly across its atmosphere. Brown and green continents form patterns shaped by mountains, rivers, and forests. Compared to the enormous scale of the universe, Earth is unimaginably small. Yet on this tiny planet, something extraordinary has happened. Life has appeared, and somewhere on its surface, a conscious being is looking up at the sky. The photon is heading directly toward that world. As the photon approaches Earth, the planet slowly grows larger until it fills the surrounding space. From above, the curvature of the world becomes visible. Sunlight reflects from the vast oceans, while entire weather systems swirl across the atmosphere like slow-moving paintings. Unlike most worlds in the universe, Earth possesses a thick protective blanket of gases, its atmosphere. For most of its journey, the photon has traveled through almost perfect emptiness. Interstellar and intergalactic space contain only a few atoms scattered across enormous distances. But as the photon reaches the edge of Earth's atmosphere, the environment changes. Suddenly, there are countless molecules surrounding it. Nitrogen, oxygen, tiny traces of water vapor and other gases. Many photons entering Earth's atmosphere are scattered in random directions by these molecules. This scattering is the reason the daytime sky appears blue to human eyes. Yet our photon slips between the molecules without being deflected. It continues forward. Below it, the surface of the planet becomes clearer. Mountain ranges cast long shadows across the land. Rivers carve winding paths toward distant oceans. Cities glow faintly along coastlines and across valleys. Somewhere on this world, a person is standing outside during the quiet hours of the night. Above them stretches a sky filled with stars. Among those stars is the faint band of light created by billions of distant suns, the glowing arc of the Milky Way Galaxy itself. The human observer does not realize that one tiny particle of light is racing toward them after traveling across unimaginable distances. The photon continues its descent through the atmosphere. Soon it reaches the final thin layers of air just above the ground. Its journey is almost complete. The photon moves silently through the last meters of air and finally reaches the surface of Earth. There, standing beneath the night sky, is a human being. They are gazing upward in quiet wonder. For thousands of years, humans have looked toward the stars and asked questions about the universe. They have built telescopes, written stories about the cosmos, and sent spacecraft beyond their planet. Yet at this moment, the observer is simply enjoying the beauty of the night. The photon travels the final distance and enters the person's eye. First, it passes through the transparent outer surface known as the cornea. Then it moves through the lens of the eye, which focuses incoming light toward the back of the retina. The retina is covered with millions of specialized cells designed to detect light. When the photon strikes one of these cells, something remarkable happens. The photon disappears. Its energy is absorbed by a tiny molecule inside the cell. That energy triggers a microscopic chemical change, producing an electrical signal. The signal travels through a network of neurons and eventually reaches the brain. And in that moment, something extraordinary occurs. Light becomes perception. The human observer suddenly becomes aware of a faint point of light in the sky. Perhaps it is a distant star. Perhaps it is the reflected glow of a planet. The observer cannot know that the photon responsible for this moment began its journey millions of years ago. But the brain interprets the signal as a tiny spark of light against the darkness. A star appears. The journey of the photon has ended, not with destruction, but with meaning. It has become part of a thought, a moment of awareness, a connection between a conscious mind and the universe. The story of this single photon may seem small, but it represents something much larger. Throughout the universe, stars constantly release unimaginable numbers of photons. Every second, the sun sends vast streams of light outward into the solar system. Some of those photons warm the surface of Earth. Some reflect from oceans, clouds, and ice before returning to space. Others continue traveling outward forever, leaving the solar system and drifting into the depths of the Milky Way Galaxy. A few may eventually escape the galaxy entirely, entering the enormous darkness between galaxies. Over millions or billions of years, those photons may cross unimaginable distances before finally encountering another star, another planet, or perhaps another intelligent observer somewhere in the cosmos. In this way, light connects the entire universe. When astronomers study distant galaxies, They are observing photons that began their journey billions of years ago. Those tiny particles of light carry information about the stars that produced them, the gases they passed through, and the age of the universe itself. Without photons, the universe would be invisible. With them, it becomes a story written across space and time. And every time someone looks up at the night sky, countless ancient photons complete their journeys by entering human eyes. Some began traveling long before civilization existed. Some began before Earth itself formed. Each one carries a small fragment of the universe's history. The photon in our story has now become part of that history. Its journey ended in a moment of wonder beneath the stars. But countless others are still traveling. Across galaxies, across millions of years, across the expanding universe. And somewhere, far beyond our world, another photon may already be racing through the darkness, beginning a journey that will one day end in the awareness of another mind looking up at another sky. Because in the end, the universe tells its story through light, and every photon is a traveler carrying that story forward.